In this video, I will show you how a PWM works. So basically, a PWM is a method to generate the gate signals for the MOSFETs or the switches. Now, for this example, we will use a half bridge because it's very simple. So basically, for a half bridge, we have an input voltage and an output voltage. So we want to generate this output voltage by controlling the gate signals. So quickly, the output voltage is Vmx, and this is equal to the input voltage multiplied with the gate signal. So you can see that when the gate signal is 1, this voltage is equal to this voltage because then it's closed, so all the current flows through the switch. And when it's 0, this is open. And when it's open, no current flows through here. All of the current flows through this switch instead, which means that this voltage here is equal to this voltage. So then you can see that it will be the same as multiplying with the gate signal. And now one problem with this equation is that the gate signal is binary. It's either 0 or 1. And for a controller, that is hard to deal with. So a common solution is to have an average model instead. We define a duty cycle, which is basically the average of the gate signal. So for example, if we want the gate signal to be on 75% of the time, we will get a duty cycle of 75%. So we can actually insert this for the output voltage. So we get it's equal to V in multiplied by the duty cycle instead. And now if we have a desired output voltage, we can actually calculate the duty cycle. So we get Vmx over the input voltage. And now we are able to calculate the duty cycle, but now we have to translate that back to the gate signal because that is what goes into the switches. So now we need to use a PWM to get the gate signals. So basically what we do is that we use a comparator. So the input of the comparator is obviously the gate signal, but then we also have a carrier. I will show you what that is in a moment. And we compare these two signals to get the gate signal. So if we go down, I have an example. So you can see this is the block diagram that I just wrote down. And then here we have a carrier. So the carrier is a triangular waveform with the frequency that we want. So the frequency of the triangular waveform should be the frequency of the gate signal or the switching frequency that we want. So here is a mathematical expression for the gate signal, but I think it's easier to look at the block diagram here. So you can see that when we have a duty cycle above the carrier, you can see that we get a gate signal of 1. And when it's below the carrier, then we get a gate signal of 0. So that is basically how a PWM works. And now we can adjust the frequency of this carrier to adjust the frequency of the gate signal or the switching frequency that we want. And now you can see that we can actually generate whatever signal that we want. So if we go down a little bit more, and you can see that we have an example in Python here. So if the input voltage is 400 volts, and then we have a reference voltage, this is the desired Vmx, the output voltage that we want. So you can see that it's sinusoidal with an offset. So it should be floating around 200 volts with a ripple of 100 volts. And then we have a switching frequency of 1 kilohertz. And we use that to generate a carrier, which is triangular. So this is just a fancy way of writing a triangular waveform mathematically. And now further, this Python script generates the PWM here. So first we calculate the duty cycle, and then we calculate the gate signal. So this here is just a comparator. And then we calculate the output voltage. And we also have a moving average, which is just a perfect filter. And then we plot the functions. So now these are the results that we get. So first we can look at the reference voltage, we wanted the output voltage to be equal to the dashed line here, the green dashed line. So you can see that it is sinusoidal and on average 200 volts. And then we can calculate the duty cycle to see that we get also a sinusoidal with an offset. And now, if we look at when the duty cycle is 50%, the gate signal should be just as much on as it is off. And you can see that it is. And when we go here, it's more on than it's off. And here it's equal again. And here it's more off than it's on. So you can see that the gate signal kind of like makes sense from what we expect. And the orange curve here is the average of the output voltage. So it's the average of the blue curve here. So you can see that that matches the desired output voltage that we want. So you can see that the carrier works very nice. Now remember that this is a perfect average. You will not be able to do this in real time. Now in my next video, I will show you how to make this in Simulink. Now this PDF here is a part of a mini course where I explain 3 different PWM strategies for a full-bridge inverter. So it's a bipolar PWM, and then a standard unipolar PWM, and another type of a PWM. So I will explain all of those and also compare them. So I will also make videos for each of these topics in the future. Now, if you want this, you can just go to the link in the description.